Hello everyone, I'm Dr. Chris. I'm here with my science helper, Max.
Hi.
Today we're going to learn about Newton's laws and some physics by doing experiments and activities. We're going to read a book and we may even watch a video. If you have the box at home, then you'll find all of these things in the box. And from home, if you have the box, you'll also need some scissors. And over here we have some things that we're going to weigh with the spring scale. First, I want to tell you a little bit about who this person is up here. Do you know who that is? Newton. Sir Isaac Newton. Is he alive? No, he's not alive. Sir Isaac Newton lived over 350 years ago, and he was the first person to use mathematics to make theories of physics. Isaac Newton was an English physicist and mathematician. And in fact, when Newton was alive, there was a pandemic during his time as well, and he had to leave the university and go home and be isolated there, just like many of us are experiencing today. During that time, Isaac Newton saw an apple fall from a tree, and that's what gave him the inspiration for his universal law of gravity. Now, I want to show you a little story of Isaac Newton right now.
Isaac Newton, Isaac Newton. Let's learn with our friend Isaac Newton.
Newton was a scientist who lived in Britain more than 300 years ago. In those days, science and technology was still very underdeveloped. There were no cars or planes, no electricity or telephone. People traveled on foot or by carriage and used candles for lighting at night. Later on, with many of Newton's discoveries, the world changed a lot. That's why we say Newton is a great scientist, just like a streetlight at night shining on the roads of human development. With Newton's discoveries, scientists have since invented cars, planes, trains, and satellites. I tell you all that I have proven that gravity is universal. It is on this page. Newton was born in a farmer's family, just like many other kids. He was very little. He was so small, he could even fit into a pot. His whole family was quite worried whether he would even live. Nobody could have ever predicted that this little baby would turn into a great scientist who changed the world. Newton lived a bitter childhood. His father passed away 3 months before he was born. When Newton was 3 years old, his mom remarried and left home. Newton was raised by his grandparents until he was 11 years old. He often got bullied at school, so he would rather play by himself. Doing experiments had become a lifelong hobby for Newton, in which he also found many great science discoveries. Some of his great findings include gravity and Newton's laws of motion.
Let's learn with Dr. Chris.
I hope you liked that little video of Isaac Newton. Isaac Newton was able to unify gravity and come up with some laws of motion. And we're going to learn about those later. But the most important part of the laws of motion are force. Force, as Max told us, is a push or a pull. Now, I'm going to write some vocabulary down on the board so we can remember these words. So we have force, which is a push or a pull. Now, in order to feel these forces, you can play a little game at home with your parents. Max and I are going to play the game, and you can play along too. The first one is a pushing game. So Max and I are going to play a pushing game, and we're going to see who has the stronger push. Max won the pushing game. Now we're going to play a pulling game. Here I have a rope, and Max and I are going to play tug of war. You ready? Oh, he won that game as well. So you can play the pushing and pulling game at home, and that will allow you to feel these forces. So the game is tug of war, and that's a game of pulling force. I want to ask you, do you know any examples in your life of these pushing or pulling forces?
Pushing a pen.
Ah! Andrew pulled the lid of the pen off, and I saw him push it back on.
Opening a door and closing the door.
Opening a door and closing a door. So, which one is a pull? Is that an open or a close?
Close.
Yeah, it depends on which side of the door you're on. Sometimes you can push it open, and sometimes you can pull it open.
You like push. You like putting something back. It's like push is like putting something back, and then a pull is like taking it, like taking it off.
That's very good.
My door just opened by itself when I go outside. It just opens itself when I go outside. Sure.
Yes, well the great thing is that whenever something moves, there must be a force. So a door can't open by itself, there must be a push or a pull. And that push or pull, it could be you, or it could be a spring on the door, or it could be the wind that pushes it open. These are some great examples. You might see one when you're pushing the pedals on your bike. We're going to make our spring scale. So just a reminder, we need the materials here. And Max, you look in your box for these materials here. And I'm going to drill the hole in my popsicle stick. The scissors are very sharp, so you have to have mom or dad's help with this. Max is going to find his materials in the box. We'll do it very slowly and carefully because we don't want to break that popsicle stick. You get out your popsicle stick and your straw and your paper clips, your rubber bands. Almost through, look at that. There we go. Yes. You need scissors from home if you have the box. Scissors are sharp, remember? Did you get everything you need? Yeah? All right, I hope everyone's going well at home. Okay. So we have our hole. And we have our material. The first step is to take one of your paper clips and place it through that hole and just leave it just like that. And we need a rubber band to go around that as well. Can you put a rubber band into the loop of the paper clip? You got it? Okay. So the rubber band and the paper clip, they're going to look like that. Does everyone see that? Okay. So you can hold your spring scale by the paper clip, and that's the rubber band that's going to measure the force. Okay? Now hold that down because you want to measure the length of that rubber band. So I'm just going to hold it down just like that, not stretch it though, just hold it. And we want to see how long it is because we're going to cut our straw to be that length. So you get those scissors from home and you want to cut the straw the length of that rubber band. There we go. You try it again. You try it again, I'll catch it this time. When you snip the straw a little bit longer than that, remember? The length of the rubber band. I'll catch it. Here we go. Now, somehow, you need to get that rubber band into that straw. And the way you can do it is by fishing it out with another paper clip. You want to use one of these? You want to save that one for later? Here. So, straighten out the paper clip, leaving a small hook on one end. So here I have a straight paper clip, and I've left a small hook on one end. And what you're going to do, yeah, you can do it that way. I'm going to push the hook through first. So here I've pushed the hook through. And then I'm going to wrap the rubber band on my popsicle stick around that hook, and I'm going to pull it through the straw. Okay, now leave that there just like that, and take another paper clip, and you can just hook that through the rubber band that's sticking out of the bottom of your straw. So open it up just a little bit like that, and hook it through the rubber band. And then you can remove your fishing hook paper clip, and now you have a paper clip sticking through the bottom of your straw. Let's see yours. Does it look like mine? Yeah. There we go. Now look at that straw. It's kind of dangling there. So we can keep the straw fixed to the popsicle stick by using more rubber bands. So what you need to do is you need to put a rubber band around the popsicle stick and twist it as many times as you can. After you get a few twists, maybe mom or dad can help you with the last few twists. You want it to be on there nice and tight. So there's one. For me, you got one. Very good. And here's the second one. I'll put one near the top, and then I'm going to put a second one near the bottom of the straw. Round, twist, and around, twist, and around, twist. How many did you do? Did you count? I wasn't counting. 6, 7. Oh, I think that's all I can do. Maybe 8. Oh, I got it around 8 times. There we go. And that's the basic popsicle stick spring scale. Now let's review the steps. Step 1, we drilled a hole. Step 2, we put the paperclip through the hole. Step 3 was we put a rubber band around the paperclip. Step 4 was to cut the straw the length of the rubber band. Step 5 was to use a fishing hook paperclip to fish the rubber band through the straw. Step 5 was to put a paperclip around the bottom of the rubber band. And then the final step was to wrap 2 more rubber bands around the straw and the popsicle stick. And that's your basic spring scale. And you see it has a little hook on the bottom there as well. Now, a regular scale at a supermarket, a spring scale at a supermarket, will have markings so that you know how much the food that you buy weighs. But we don't have any markings yet. We're going to make our spring scale look like the finished product. Now, our finished product, it has some decorations. We've already made some decorations on our finished spring scale, and you can do that at home. But one thing we're going to do right now is make these markings. So, you'll notice that on our final spring scale, not only do we have markings, but we've bent the paperclip so that it measures where on the spring scale we are. In order to do that, you need to take that paperclip at the bottom and just twist it to the side so that it is pointed sideways. Now wrap it around so it makes kind of like a loop. Wrap that one around the other side. So let's have a look at yours. Let's just hold on a second. Oh, you got it? So let me show everyone Maxwell's. You need to take the smaller loop of the paperclip and just twist that up. And if you want to make it stay on there a little bit better, you can twist it around and you'll make a little loop on the paperclip. See that little loop there? And that's right where the rubber band will sit. So inside of your straw you have a rubber band and it's going to look like this. Okay. How are we going to make the units? Okay, to calibrate a spring scale, you need to weigh something that you already know the weight of. And you can do that with a kitchen scale. So if you have a kitchen scale at home, then you can put anything you like on there and you can determine the weight of that thing. So an apple weighs 210 grams. Or if you don't have a kitchen scale and you just have a product at home from the grocery store that's in plastic, in some packaging that doesn't weigh very much, then it will tell you how much it weighs right on it. So here's some cat food, and that cat food is 90 grams. That's a pretty good meal for a cat, eh? 90 grams of protein smoothie. Does that sound good? Can you try it? No? Okay, so I know that this weighs 90 grams. So when I place it onto the mask, so you want to get your mask out, and you can make a little basket for whatever you want to weigh. Okay, so I've made a little basket, and I know that this weighs 90 grams. I can feel 90 grams. And are you going to use the apple? Do you remember how much the apple weighs? 210. Okay, you want to get it in there, wrap the mask around it. You want some help with that? Make sure the mask is open. There we go. And hook it onto your spring scale. Get it on there. Very good. So here you can see on my marking that is 90 grams. So you can do it by yourself if you have two good hands, or you can use mom or dad's help, and they can mark on your spring scale 90 grams. And you can do that with lots of other different weights. So I can write 90 on there. So I wrote 90. So now let's switch. Did yours go past the marking? Yours went past. Yeah. So there's 90. Let's try something else. Let's try an orange. The orange weighs 121 grams. And here's a test for you. When I put the orange into my basket and put that on my spring scale, is it going to go further than that line?
No.
It's going to be above the line?
No.
It's going to go down further. See? Yeah. And why is that? So that 126. Is that larger or smaller than 90?
Larger.
Larger. So the gravity is less or more?
Gravity is
More, yeah. So it's going to pull on that more. Let's see. And there you go. It's below the other line. So if I like, I can put another mark there. And that one is 120. There we go. So now I have a calibrated spring scale. So you can do that with lots of things that you know the weight of, and then you can mark it on your scale, and then you can start to weigh some things that you don't know the weight of. So here I have another. I think this one's heavier. Just by holding it in my hand, I feel like that one's heavier. It looks bigger. Let's put it on the spring scale. And look at that, let's let it sit. And yeah, look at it. It's below 120. So the force of gravity is more for this larger orange, and so it pulls down on the spring scale more. So this spring scale is measuring the force of gravity. Heavier things, the things with more mass, feel more force of gravity. And so they measure higher values on our spring scale. So let's put this on the kitchen scale, the accurate kitchen scale, and you see this definitely weighs more. This one was 120 grams, and this one is 133 grams, and our spring scale measured that for us. All right, let's have a look and see if anyone else is measuring some things on their spring scale. That's very good. So while you continue putting your markings on the spring scale, you can decorate it if you wish. And remember, here, I don't know if you can see that. If we zoom in, you can see we've got some eyes, some hands. You can decorate it any way you like, and you can keep that spring scale for later to measure the weights of things that you might have around the house. Now, we're going to quickly summarize. So, we had two more things that we need to write. So, a spring scale works because of a spring. So, a spring is something that deforms its shape under a force. And we can use that to make a spring scale. Okay, so let's remember our vocabulary words for today. We have force, push, pull, tug of war, spring, and spring scale. Now, the key things that we learned today about force are that it's the basic concept that Newton used to make his laws of motion and all of his theories of physics that we use today. It's through this study that Newton found the laws of motion, and he's also the first scientist to start to describe physics with mathematics. So remember, force is a push or a pull, and the most important things about force are how big it is. That is what the spring scale measures. It measures how big the force is. And the other important thing about a force is the direction. So a push is a force that's pushing away from you, going away from your body. And a pull is something that's coming towards your body. But there can be a direction to any force, and it can be in any direction. So the wind has a direction, so it's pushing things along, and that could be pushing up, or it could be pushing to the side, it could be pushing down. The direction and how big it is are the two things that tell us about the force. Okay, so I have some questions. The first one is, what is a force? A is force is a push or a pull. B is force is big or small. It looks like everybody has it correct. Force is a push or a pull, and these can look very, very different. So there's a pushing force on my hand. I can feel the weight of that apple, but the apple is being pulled by gravity. So there's pushes and pulls everywhere where we see a force. Okay, next question. It looks like everyone got that one right. What part of the force does a spring scale measure? Does it measure A, how big the force is, or B, the direction of the force? Let's see here. That's right. So A is the correct answer. When we have a spring scale, the direction is always pointing down. So we don't need to know the direction of the force. The direction of the force is always down. What the spring scale measures for us is how big the force is. And we can measure things like our food at the grocery store with the spring scale, so we know how much to pay for it. Okay, great job. The final question. When we were playing tug of war, which direction are the competing forces? Let's say that A is, it's the same direction, okay? The direction of the competing forces is the same direction, either both left or both right. And let's say answer B is the opposite direction. Do you think it is the same direction? That's A. Or do you think it is the opposite direction in tug of war? That's B. Let's see what you think. B is the correct answer. So when we had a tug of war, we have our tug of war rope right here. Max, you want to grab it? Max has been busy decorating his spring scale. So we're pulling. Max is pulling towards him, and I'm pulling towards me. It's opposite directions. Max wins again. All right, very good. I think almost everyone got the correct answers, so I hope that those key learning elements are what you can take home with you and use when you're playing with your spring scale. All right, very good. Next, I want to read a book about forces. Okay, and this book is in the series Red Kangaroo, 1000 Physics Whys, and it's called Newtonian Physics, Tug of War. Okay, so we have Red Kangaroo and his father. And Red Kangaroo says, when I play tug of war with Dad, he always wins. Can I use physics so that I can win next time? What do you think? Red Kangaroo use physics? Red Kangaroo likes to go visit Dr. Chris in the lab to get the answers to the questions. And Dr. Chris tells Red Kangaroo, you need to understand who can pull more, and that's who will win. You need to understand the force to answer your question. And force is the core concept in physics. And Red Kangaroo says, of course, I do that every day. I pull the door open and I push it closed. And those were some of the examples that you gave me earlier. Dr. Chris says, there are more forces than just the push or pull of your own hands. Can you think of a pull on you that never touches you? I'll give you a hint. You have to jump to feel it. Red Kangaroo knows it's gravity. And Isaac Newton knows too. The story goes, he had an apple fall on his head, and that's when he thought about his universal law of gravity. But that's not probably true. Well, we don't know. But I doubt very much that Newton let an apple hit his head. How's your apple tasting? Which force are you using to eat it? The force of your mouth, your teeth? Very good. Okay. Dr. Chris says, gravity is an invisible force that pulls everything together. The bigger things are, the bigger the pull. Red Kangaroo is right. And he says the Earth is very big. So big that it's stopping him from jumping really high. So there's a force of gravity between every two objects, but the Earth is so big that it's really the only force of gravity that we can feel. I can't feel the force of gravity between myself and Maxwell, even though there is a force of gravity between us. Red Kangaroo says, I know the name of these forces, but how can they help me win tug of war? The most important thing is the strength and the direction, Dr. Chris tells Red Kangaroo. Forces with the same strength in opposite direction cancel each other out. Red Kangaroo says nothing happens. When Max and I initially played tug of war, the rope didn't move, so we must have been pulling with the same force. Red Kangaroo says, what if I pull with more strength? Then Red Kangaroo will win. Dr. Chris says, now you can find out the answer by drawing arrows. First draw all of the pushing and pulling forces that you know. Now move the arrows like they are the directions on a map. Line them up, tail to tip, and you can draw a new arrow that tells you the resulting force. So we have a picture here of Dad with a big arrow because he has a big force, and Red Kangaroo with a small arrow because he has a small force. And we can add these two together to see that Dad wins. Dr. Chris says, now look at this picture of you and Dad playing the physics of tug of war with your force arrows. You add them to find the true force, and that is called the net force. Red Kangaroo does it and shows the net force arrow is pointed in Dad's direction. Adding up force arrows to find the net force is easy. But what about the opposite problem? Can you find the right force and direction to best Dad at tug of war? I think Red Kangaroo can do it. Red Kangaroo says, I found it. I have mastered the physics of force. And you see that he's drawn a bigger force arrow for himself and a small force arrow for Dad, and has added these forces together to show that he won. And how did he get a bigger force arrow? He had Mom's help. And that's the end of tug of war. Okay. Well, I hope you enjoyed that story, and I hope that you've had a little bit of time to decorate your spring scales and have shown your markings to show how much weight is being pulled on your spring scale. So let's take a look now to see some examples of your work. Now you can see some pictures of everyone's work on screen. You've all done a great job making these spring scales. Okay, Vicky, do you have a question? You got some nice stickers on there. You weighed something that was...
77 instead of...
Oh, 77 and 100. Very good.
Do we need rice?
Oh yeah, you can weigh some rice. Let's find out what a cup of rice is. And that's 63 grams. And I can take rice out to reduce the weight of this, and I can get really accurate measurements on my spring scale if I use rice, because I can make the rice weigh anything I want.
But what happens if you're playing tug of war with two children that are divided by 2 plus 1 for their age, and you pulled as hard as you could, then who will win?
So you need to find out how much force you can pull with and how much force your friend can pull with, and you add those together, and if I can pull with a bigger force, then I win. And if you add your forces together and that number is bigger than what I can pull, then you'll win.
If you eat more, does that make you stronger to play tug of war?
If you eat more, yes, well, your muscles need food in order to grow, but you need to eat the right food, okay? So you need to eat healthy food, you need to eat what mom and dad tell you to eat. So if mom and dad tell you in order to grow big muscles, you have to eat your vegetables, then you better eat your vegetables.
I'm ready to go to cannon.
Is that canon?
You built a cannon. Oh, that's great. Let's see how it works.
I made it at school. We put a hole in it and we put the balloon, and then we pull this balloon and when we let go of it,
Very good. Now, Dylan, do you think that there's a force involved in your cannon? And where does that force come from?
the balloon.
From the balloon. Very good. A balloon is almost like a rubber band. So it has the same properties as a spring. When it gets stretched, there's a force that makes it push back to its original shape. And your balloon, you stretched it, it wants to go back to its original shape. And that provides the force, a pushing force. Look at that. Oh, you're weighing an apple? Were you able to measure how much that weighs, Alex? Cool.
150 grams.
150 grams. You see what Max did to my apple. Now, it used to weigh 210 grams. Now let's have a look. Now it only weighs 90 grams. 210 to 90. Now Max is going to be able to beat me in tug of war now. Okay, let's let Jaden ask the last question. Jaden?
Why does magnet attach to iron?
Why does a magnet attach to iron? Well, there's a force, right? So now there's a force, a pulling force between the iron and the magnet. A magnet can actually create other magnets. Iron itself is not a magnet. If you put iron up against the refrigerator, it'll just slide down. But if you put a magnet next to iron, then it makes the iron magnetic, and two magnets will pull themselves together? That's a great question. So there's 5 classes in total on Newtonian physics, and each one has their own book, and we'll learn about, in the next 4 classes, how to build some pretty exciting things. I have some examples over here for you. We're going to learn how to make a momentum cannon. The concept of momentum, and we'll build a cannon just like that. And a paddle boat here. And my favorite is the carousel. And we're going to use all of these fun things to explain Newtonian physics. Okay, I think that's enough for today on forces. Thank you, everyone, and I hope you enjoy playing with your spring scale and you learned a lot about forces and Newtonian physics. Bye!
Let's learn with Dr. Chris.